Okay, let us start today's lecture. From this week, we'll talk about the state space design of control systems. So first of all, what is a state of a system? So it is the characteristics of the system. For example, with respect to time. And then this could be, again, for example, should be the position, and then velocity or acceleration. And then usually these states are related by differentiation. Okay, the velocity is the time differentiation of position, and then the acceleration is the time differentiation of velocity. The position, velocity, and acceleration describes the characteristic of the state. For example, you're driving a car, so where your car is the position. And then how fast you drive is the velocity, and then the acceleration, that if you have to go upslope or you're going downhill, the velocity changes against time. All those properties, characterize your car, right? And then we say that it is the state of, for example, of your car. Okay, so far, is that clear about the definition of states? Right. Okay. Then, again, we recall that the frequency response and design method, frequency response. So it is a complex number-based technique. Complex number. And for the state space design, so it is the matrix algebra. Okay, from now on, we will not talk about complex number, right? Unless it is in the tutorial or in the examination that we will need the complex number. From now on, we will need the matrix algebra. And before going into the details, we have a brief review, right? Or try to recall from your memory all about matrix algebra. So in matrix algebra, we have several definitions. We have the scalar, a vector, and then matrix. So the three basic definitions in matrix algebra. Scalar, we can treat it, okay, as just a number. And then this number is not a complex number, right? And then the vector is collection of numbers. And then the matrix is also a collection of numbers. And then the difference between vector and matrix is that the collection of numbers can be 1, 2, 3, 4. So we call it a row. Right? We can also have it 1, 2, 3, 4. So we call this a column. And then for a matrix, we have, for example, 1, 2, 3, 4. One row. And then 2, 3, 4, 5, etc., etc. So it is a matrix. And then we also would have in rows 1, 2, 3, 4, okay, and then 2, 3, 4, 5, etc., etc. One important thing we need to note is that important thing is the number of row in column in the matrix. It may or may not be equal. Okay, for example, here we have 1, 2, 3, 4 rows, and then on the other hand, we can also have 5 columns, 6 columns. Okay, the number of rows and columns may or may not be equal. Then we look at, or we try to recall the basic operations. On vector or matrix. The first operation that we normally encounter in the rest of this topic in designing a control system using the state space, the operation is called a transpose. So we can treat it as a interchange of row or column indexes. So for example, if we have a matrix called 5183, if we have this one, so we can index the numbers or index the elements. So by convention, row, then column. So that then we can put it as the elements as A11, A12, A21, and A22. So for this 2, it is the second row. And then for this 2, it is the second column. And then we can also say that A is a collection of elements indexed by I and J. Okay. And then the A transpose. Okay, this is the symbol for transpose. So it is an exchange of index. It becomes Ji. Then using our our example, then the transpose is 5813. Especially for the corners, okay, this one. So this one is the 8 here. It is from second row, first column to first row, second column. And then the one here, it is from first row, second column to the second row, then we have also the first column. So this is the transpose. Okay. We also have some important properties. Is that property? If we have a matrix A and matrix B multiply together, okay, the result is this one, and it is not equal to so it says that the transpose of a matrix product so it equals to product of individual transposed matrix. Okay, it is one of the important properties that we will encounter, right, in the rest of the design of control systems. Okay, another definition or operation that we have to look into is the determinant. So if we have the A equals 12, 19, 11, 6, and then we say that the determinant of A, and then we use this symbol. Okay, this is the symbol. And the method to obtain this is 12 times 6 minus n times, okay, it is minus 137. So the rule is the northwest to southeast product, and then minus the northeast to southwest product. So it is this, the northwest to southeast, and then subtract this product. If we have the larger size of matrix, for example, if we have 3 by 3 matrix, then the determinant of B so equals to the northwest to southeast product. So it, first of all, it is 3 times 3 times 3, and then we have one product here, another multiplication, and then we add together. So we have a 9 times 2 times 3, and then the other one is this 4. So it is 4 times 9 times 10. Then we do the subtraction, the product, this way. So we subtract 4 times 3 times 3, and then subtract 9 times 9 times 3, and then also subtract the 3 times 2 times 10. And then the final result is 102. So this is the operation of the calculation to obtain determinant. Yeah. Okay. First of all, from the this one is the northwest to southeast. This part. Okay, and then the next one, 9 times 2. It is 9 times 2. What is here? Here, this one is this 3. Okay. Then we have the 4. So 4 is here. The next one is the 9 in the next row, and then the 10 here. Okay. And then for the subtraction, we just do it in the other direction. Okay. Good. Then we have some a few more definitions. Okay, more definitions. First of all, we define a minor. Okay, for example, if we are given another the matrix A equals 3, 9, 4, then 9, 3, 2, 3, 10, 3. So now we define the minor. The minor matrix of A equal to, for example, we say we use the symbol M. Right. So it is the determinant without the row and column of the indexed element. So what I mean is that for okay, we have A equals 3, etc., etc. So this one is element in row number 1 and then column number 1. Okay, agree? Then the determinant of the determinant without the row and column of the index element. So the determinant of we have 3, 2, 10, and 3. So here and here it is without row column. So the determinant of 3 or 10 to 3 equals it is 9 minus 20 equals minus 11. So this one put into row number 1 and then column number 1 of the minor matrix. So this is the definition of another matrix created on the basis of a given matrix, for example, A. Okay. Each element of the matrix M, the minor matrix, is the determinant, right, without the row and column of the index elements. Okay, if we have the first row and first column, we just ignore the first row, ignore this first column, and then we calculate the determinant on the rest of the elements. And then get the result, we put it into this location in the minor matrix. Okay, got it? Then for our okay, for the A matrix, 3, 9, 4, 9, 3, 2, 3, 10, 3. The minor is 3, 2, 10, 3 determinant, and then 9, 2, 2, 3 determinant, and then we have 9, 4, 10, 3. Okay, a little bit complicated, right? So we take look at another example, the middle one, So this one is the second row, second column of M. So it is obtained from the determinant of A without second row and second column of A. So without the second row, so we have see this. So without the second row and the second column, we have 3 and 4 in the first row, and then we have the 3 and 3 on the second row. Okay? And then the rest we calculate it using the same method. So for this example, we have the minor is 6. And another definition is called cofactor. So it is element-wise multiplication of -1 to the number of row, to the row index of row and then column. Okay. Multiplication of row with the original with any given matrix. Okay, now the cofactor, it is -1. The first element is first row, first column. So this is the first row, then first column. Then -1, 1 plus 1 equals -1 square equals 1. And then for the next one, for example, this one. So it is second row, first column. So the second row, also the first column. So we have -1, the second row, first column, equals -1 to the power 3 equals -1. So in our example for a 3 by 3 matrix, so it is 1, -1, 1. So for this cofactor matrix, so is it okay seeing how it is obtained? Okay? Any question up to now? And then we have the element-wise multiplication with, for example, our minor matrix. So it equals to this one. Okay, everybody see the logic about the -1 to the power row per column. Okay. Then another definition called adjoint matrix. This adjoint matrix is defined as the transpose of cofactor. So in our example, right, the adjoint of our cofactor matrix, so it will become the adjoint matrix, and then we transpose then the inverse of a matrix. The inverse of a matrix is defined as, for example, if the A matrix A, the inverse, it is the adjoint matrix of A divided by the determinant of A. So for A equals this one 3, 9, 4, 9, 3, 2. So the inverse is the adjoint matrix, this one. It is minus 21. It's divided by, we have calculated before, it is okay, the determinant is 102, determinant of A. So this is the inverse. It is, we will use this several matrices a lot in the rest of the design. So the important properties. Properties is different from scalars. For example, if we have the A, B, C inverse, it is not equal to C, B, A inverse. It is not, right? And then C invert B invert A invert, it is not equal to A invert B invert C invert. Okay, those properties that we have to pay attention to, right, when we are doing our controller design. Okay, that is the revision or the recall of the matrix algebra. Then we'll take a few minutes break, and then we move on to the next topic. Okay, let us continue. We again recall our from our memory, right? The control system design. It starts from describing the system using differential equations. And then one approach is to use Laplace transform to obtain the obtain transfer function. And then we can put the transfer function into complex frequency. That is, we put S equals J omega, right? And then use frequency response methods. Another way is that after getting the transfer equation, so instead of putting into complex number, we'll put into matrix equations. Then we use state space design. There's one important thing that we need to notice. Right? It is important. Right? Is that either method could produce a good designed system. So there's no such thing as this method is better or another method is not so good, right? All the methods, they are equally likely, right? It's a kind of implementation. So matrix-based approaches. It is only more suitable in computer calculations. It is just a implementation advantage, especially nowadays we have powerful computers. Then we use the matrix. Okay. Then we look at an example, a simple example. So look at the example. So we have a mass damper system. mass spring or damper system. So we have a fixed ceiling, for example, and then we have the mass, we have the spring constant, and then we have the damper constant. And then we define the position variable. And then if we apply a force to move the mass, then we have the balance of forces. So this should be very familiar so far. Put this y, put this variable the y, right? Because by convention we will use the x later on, and then we do not want to confuse the symbols. So it is the mass times acceleration is the force, the input force minus the counteracting force. Okay, the counteracting force due to the damper, and then the counteracting force due to the spring. So we take the Laplace transform. Then it is s square m, and then plus b s plus sb plus k of the ys, okay, equals f s this. Okay, the Laplace transform method, and then we'll get the transfer function. The g of s equal to s square m plus sb plus k then over 1. So it is very familiar with us. Okay. Then so the next question is how to put into matrix equations. So the first step is to define the states. For example, we can call it x1 equals y. And then we can call x2 equals y dot. So it is also equal to x1 dot. Okay. Then we can have rewrite the differential equation. Then we have the y dot t equals x2 dot t. So it is equal to minus b divided by m, and then x2 t k, so x1 t plus 1 of m, and then f of t. It is a redefinition of the variables. Here, the x1, in fact it is y1. And then for x2, in fact it is y dot. And then if x2 is y dot, and of course x2 dot is an additional differentiation on y, so we have the y dot dot. Yeah. So we note that, okay, it is just a rename or a rename of variables in the differential equation. Okay, we just rename the variables. In fact, they are the same thing. Okay, any question on this? Okay. Then arrange the states as vectors. So in our example, we have x1, x2, and then this one is the state vector. Sorry. Because in the matrix algebra, we have scalar vectors and matrix. So the first step is to put the states into vectors. And then equate the left-hand side, left-right side of the differential equation. So we have x1 dot, x2 dot. So it equals a matrix to be constructed. So first of all, we look at x1 dot. Okay, x1, the x1 dot equals x2. So based on this equation, so it is this. So it is based on x2 equals x1 dot. Okay, then for the second part of the state, x2 dot is this one. So x2 dot is this one. So the second part, this part, this part is based on the equation xt dot equals minus b of m xt minus k of m x1, and then we have plus 1 mf. This part is independent of x1, x2. So we temporarily ignore this part first. Then x2 dot equals minus k divided by m multiplied with x1. So we have here this position k of m. And then on the other position, it is minus b of m. Then we further have we can further have the input term equal to plus something multiplied with the f. And then we see that it is related. This is related to x2. And then, but not x1. So not related to x1, we have 0. And then related to x2, we have a 1 over m. Okay. So what we have now, so we can say it is an x dot equals a x plus b and then u. Where there are u equals f is the input. And then x is the state. Okay. Finally, we have this one is in the form of a matrix equation. Okay. Okay. Know how to construct the matrix equation, right? From a given system, we have the differential equation, right? From the differential equation, we define state variables, and then we match the equations to construct our matrix equation. Okay. Any question up to now? Okay, then we ask ourselves an important question. We ask ourselves an important question about So the question I want to ask is how to define for example x1, x2 Are there any rules or systematic ways? In the previous example, right? In the previous example, let us take a look again. Here we define the y as x1 and then y dot x as x2. Can we define y as x2 and then x1 equals y dot? It is equally valid, all right? But the answer to the question is that, in fact, there are systematic ways that we can do it. And there is also other forms of the matrix equation. So the answer is yes. But there are more than one form of the matrix equation that can represent the system. Okay. Then we look at examples. One of the way to construct the matrix equation. So we consider, suppose we are already given the transfer equation, right? The output U is, suppose we have this one. Suppose from the differential equations, and then we take the Laplace transform and we arrive at this transfer equation. So the steps or the procedures that we will follow is that we identify the maximum power of S. So in this example, from the denominator, so it is S cubed plus 6S squared plus 8S. Okay, we multiply out this S into it. And then the maximum power is of S is 3. Okay, see this because of this 3. Then the next step is divide our numerator and the denominator by S3. Then we have then the transfer function becomes one plus 6 6s minus 1 plus 8s minus 2 plus 3s minus 2. This one. We just transfer the transfer. We just change the transfer function from this form to another form. And then we make use of the fact that in Laplace domain, integration is equivalent to 1 over s, and that is s minus 1. The important thing here to know is that in practice, differentiation is sensitive to noise. Hence, integration is more preferable. Okay, I agree with this statement. Differentiation is more sensitive to noise. So if we have the signal or whatever, so if we have the noise, so if we differentiate, so it will be even larger. And then if we integrate, it would become smoother. Right, see the difference here? The differentiation and integration, the integration is more preferable because of the noise effect. Okay, up to this point, is that okay? So now we rearrange the y of s, so it becomes s minus 1 plus 3s minus 2. And then we have our 1 plus 6s minus 1 plus 8 minus 2. We just rewrite the transfer equation, right? Put the denominator on the left-hand side to the right-hand side. Then we define another variable. So which is on the right hand side, we define it as this one. So which is effective just the second term on the right hand side of the previous equation. Then we have the y(s) equals s minus 1 plus 3s minus 2 plus s minus 3. Then v of s. Then it equals to s minus 1 vs plus 3 s minus 3 vs. Okay, and so far follow this. Now we note that S1, S minus 1, S minus 2, S minus 3 are successive integrators. Okay, agree? So if input to the integrators is Vs, then what we have is that we have the V of S input and then one integrator, so it becomes S minus 1 Vs. Okay. Then another integrator, so S minus 2 Vs. And then another integrator, S minus 3 Vs. Okay, agree with this block diagram, right? The signal input is Vs, then integrator, we got this. Another integration, we got this. Another integration, we got the S minus 3 of Vs. Then what is Y? Right. Then construct signal Y of S. And then we take a look at this equation again. So we have S minus 3 of Vs contributes to Y is. And then S minus 2 Vs scale by the factor 3 and then add to the others. So there is a factor of 3. It is S minus 2 and then we have another, the third term or the first term here, S minus 1 of Vs, this one. Another addition. Now we have Ys this way. Okay with this? Then we recall that Vs equals 1 plus 6 minus 1 plus 8s minus 2 Us, where the U of S is the actual input. Then Us equals Vs plus 6s minus 1 Vs plus 8s minus 2 Vs. Okay, we just put the denominator to the left hand side. Then similarly, we treat the U of S as the input. Then we have the U of S here. It is equal to the summation of these three terms. So we have a summation. Then we have the Vs here. And then we integrate. So we S minus 1 Vs. And then another integrator, S minus 2 Vs. At this point, at the Vs, this point, we can rewrite this equation as U of S minus 6 S minus 1 Vs minus 8 S minus 2 Vs equals Vs at this point. So we have the U of S addition. And then we have the minus 6 from the S to the power minus 1. So we have a minus 6 here. Add together. And then for this term, S minus 2, it is this term. So we have an 8, minus 8. Also an addition. Okay. And then we combined, we will combine these two diagrams, this one, and then the previous one, this one. If we combine them, then we have so we combine the diagrams. We have the U of S go in, and then with the V of S. Another integrator, another integrator. From the previous diagram, we have the y of s output, and then we have the scaling factor 3, and then also from here, that is from the first diagram. In the second diagram, we have -6. And then we have the -8. Like this. So this is the diagram representing the transfer function for y of s divided by u of s. This is the diagram. Then define states from out to in. So what we mean by out to in is that we define this is x1, and then x1 dot, x2 dot, x3, and then x3 dot. So we define the states this way. All right? Okay, we also note that now we have v of s equals x3 dot. So from the labeled diagram, we have x3 dot equals u minus 6 x3 minus 8 x2, and then okay, independent of x1. And then also see that x2 dot equals x3, and then x1 dot equals x2. Okay, these two variables are equal. Now, the final stage is to construct the matrix. Okay. Construct the matrix equation. So we have x1, x2, x3. So equals some matrix multiply with our state plus another matrix multiply with the control input So how to fill in those elements in the A matrix, right? So x1 dot equals x2, independent of x1 and x3. So we have this one. Okay. It is this equation. And then for the x2 dot equals x3, independent of x1 and x2. So we have a 0, 0, 1. So this part, or this row, corresponds to this equation. Finally, for the x3 dot, we have a u that affects x3 dot only, and the scale is 1. So it is 0, 0, 1. 0, 0, 1, it is this part corresponds to this. And then for the other part, so we have 0, minus 8, minus 6. So this is our state equation. And then we also see that y, the output, equals x1 plus 3x2 plus x3. So it is here. So y is x1 multiplied with the scale factor of x2 and then also the x3. So we have this equation. Then y equals is 1, 3, and 1, a matrix multiplied with x1, x2, x3. Okay, so we call it the C of x, and this one is called the output equation. So this is one of the methods, right, to construct a block diagram, and from the block diagram we can have the system's equation expressed in matrix form. Okay. Any question up to this point? So any question? Or okay, if no question, then we will look into another method. So for another method, we consider the same transfer equation. We consider the same equation. Consider the same transfer equation. So that is y of s, e of s. So we try to factorize the denominator. Factorize the denominator, this part is squared plus 6s plus 8. So it becomes, completing the square, we have minus 6 minus 6 squared minus 4 times 8. Then divided by 2. So it's minus 2 and minus 4. Then we put the denominator, the part of the denominator, put it as s plus 2 and then s plus 4. So we can also factorize our numerator. This part is squared plus 3s plus 1. Then s equals minus 3 minus 3 squared minus 4. So for this expression, right, the result is a bit complicated. Okay, we just take 2 digits after decimal. So we have this. And then 2.62. Then we can put the s squared plus 3s plus 1 equals so we have 2 factorized forms. Then the transfer equation becomes in multiplicative terms, then it is s plus 2 so we have this form. So this part and this part, okay, it can be interchanged. We put this factor to the second term, or we put the factor of 0.38 to the last term. In fact, it is the same transfer function. Then we recall that we call another term. We call a GS, okay, equals YS. Okay, which is a general form. So this one will be 1 plus b s minus 1 1 plus a is minus 1. So this form is very familiar to us, is it? This form. To the power s to the power minus 1 or minus 2 or minus 3. This form, we just have the block diagram developed for these forms. Okay. Then following the method that we discussed earlier, so we have now the y of s equals 1 plus b is minus 1, and then u of s 1 plus a is minus 1. So we have this form. So we also put it into okay, we also define an auxiliary variable, the v of s. So v of s equals 1 minus s e of s. So based on these two equations, right, we can construct a block diagram for this kind of factors. Okay, it is one of factor like this, another factor like this. So from the definition, so minus 1, so we have Vs plus As minus 1 Vs equals E of S. Okay, then the V of S equals U of S minus A is minus 1 V is. So now we construct the block diagram. So S, 1 of S is minus 1 Vs. So far at this stage we have the U input, and then we have the minus A, this factor. So this part, this factor is from this. Okay. And then we recall Ys equals 1 plus B is minus 1 Vs. And then we can put it into this form. It is V of S plus Bs minus 1 Vs. So the block diagram becomes this part. Okay. We scale with a B. So this part is this part. And then we add together. Sorry? Okay. sorry. Okay, this part, the blue. Okay, this part. Then finally we add another term, which is the V of S. So this part is here. And then this is our output Y of S becomes, so our diagram becomes this. This diagram is for the form. The form is S plus B, S plus A for this form. So here we can see that the B here, okay, it is a series scalar, series scaling, and then the B, it is the negative feedback. Then combine all terms. Combine all terms is that the transfer function is 1 over S plus 0.38, S plus T multiply of S plus T.62, S plus 4. So we have integrator. So it is 0.38, this part is scaling.